this is in curved coordinates. So let's begin by writing. So let's suppose that we have a function x, so which is also a function of q1, q2, q3. Then with y, which is a function of q1, q2, q3, and z, which is a function of q1, q2, and q3. And let's suppose that we have the inverses functions like q1, which is a function of x, y, z, q2, which is a function of x, y, z, and q3, which is a function of x, y, and z. So I can represent any vector v, for example, in q1, q2, and q3 unit vectors, like v, which is q1. So this is the unit vector q1 hat, v1 plus q2 hat, v2 plus q3 hat, v with v3. Now we can take the total differential of x, so which is x q1, q2, q3. So the total differential would be dx, which is partial of x partial of q1 dq1, partial of x partial of q2 dq2, plus partial of x partial of q3 dq3. So we can write the same thing for dy and dz. So the same thing, partial of y partial of q1, q2, and q3, of course. So, but we can represent also in a vector notation like dr. So dr would be the sum. So the sum partial of r partial of qi dqi. This is in vector notation. Now let's begin by writing the line element in Cartesian coordinates. So the line element ds squared is dr times dr, which is here dx squared plus dy squared plus dz squared. But in other coordinates, so we had that, so we wrote that dr is partial of r, so the sum of I partial of r partial of qi dqi, and dr partial of r partial of qj dqj. So now we can write that ds squared, which is dr times dr, so there are a sum of I and j of partial of r partial of qi partial of r partial of qj dqi times dqj. So in this so if here we are working in three-dimensional space, which means that we have 9 components, like partial of R, partial of Q1, partial of R, partial of Q1, dq1, dq1, so dq1, dq1, plus partial of R, partial of Q1, partial of R, partial of Q2, dq1, dq2, plus partial of R, partial of Q, so those have vectors, Q1, partial of R, partial of Q3, dq1, dq3. And we have, so here one component, but it begins with 2, 1, 2, 2, so this is partial of R, partial of Q2, partial of R, partial of Q2, dq2, dq3, plus those terms. So here's a plus the, so it begins with partial of R, partial of Q3, Q3 1, Q3 2 here, and then here we have partial of R, partial of Q3, partial of R, partial of Q3, dq3, dq3. Now, those coefficients here, so I can write in blue those here, those we call metrics. So for example, in special relativity or general relativity, they represent the curvature of space-time. So those represent the curvature. It not directly represent, but first of all we have to find those metrics, and by finding those we jump to the Ricci tensor and Riemann tensor, Riemann curvature tensor. So we can write that ds is, so ds squared is ij partial of R, partial of qi, partial of R, partial of qj, dqi, dqj. And we can write those coefficients as gij. Those are metrics. So and gij, dqi, dqj. And let's say that we write gii is equal to hi squared bigger than 0. So and we also need to define one symbol, which is called Christoffel symbol, so which is qi hat times, so this is the dot product, qj hat is equal to delta hij, which is equal to 1 and 0. 1 is if I is equal to j, and 0 is if I is not equal to j. So those terms here, so this product is 1, but this is not 1, so this is 0, 0, 0, 0, so this is 1, this is 0, this is 0 and this is 1. And now so we can write that, we can write the line element. So if G so G11, G22 and G33, so we can write that ds is equal to h1 dq1 squared. So because G11 is h1 squared, and dq1 times dq1 is dq1 squared, so this goes in squared, plus h2 dq2 squared plus h3 dq3 squared. And also in summation notation, so with sum we can write that I goes from 1 to n. In our case the n is equal to 3 for 3 dimensions. hi times dqi square. This is the line element of in any coordinate system. So now we have to write the line integral. So we have to write the line integral. So sorry, line, which is any vector v times dr. This would be so v has those components, and dr is equal to, so only one dr is h1 dq1 q1 hat, so in q1 direction, plus h2 dq2 q2 hat plus h3 q3 dq3 q3 hat. So the line integral now, this v times dr would be the sum of I, the integral of vi hi dqi. So this one can be write that as integral of v1 h1 dq1 plus integral of v2 h2 dq2 plus integral of v3 h3 dq3. So this is the line integral in curved coordinate system. Now we have to define the area element. So there is some area, and we have to find the element of that in differential form, of course. The area element. So if we have two vectors, for example a and b, so if we have two vectors, a vector and b, say b, so the cross product between two vectors, so between those two, so a cross b So A cross B represent the surface which they make. So the sometimes make the square and some different they make some different shapes. So let's start by writing d sigma. So this is d sigma. So partial of r partial of qi dqi cross partial of r partial of qj dqj, which is equal to partial of r partial of qi, which you can find it is hi dqi, and this one is hj dqj. And now we have so we have the unit vector. So this is, sorry, roof. So now becomes hi dqi qi hat plus cross product hj dqj qj hat. Now d sigma would be hi hj dqi dqj, and the cross product between those two unit vectors, qi hat times qj hat in vector notation. So I'm writing that qi cross qj is epsilon ijk times qk, and this epsilon is Levi-Civita, so Civita symbol, Levi-Civita symbol, which is a kind of tensor, symmetric tensor, which has some values depending on what system are you using. So in our coordinate system, it may have only ijk, so it has only three values, so +1, -1, and 0, so which they go with permutation. So 1 2 3, 2 2 3 1, and 3 1 2, so something like that. And so this is the area element between those two vectors. And now we have to represent this area in so like ds d sigma, which is ds2 ds3 q1 plus ds3 ds1 q2 plus ds1 ds2 q3. Now becomes what we wrote earlier, which is h2 h3 dq1 dq3 in q1 unit vector plus h3 h1 dq3 dq1 q2 unit vector plus h1 h2 dq1 dq2 q3 unit vector. So this is the area element. And now we can write the surface integral, like for example, so um, a surface integral, which is for some vector v times d sigma. This vector v has its own components q1 v1 plus q2 v2 plus q3 v3 dot product, this one. So we write only d sigma, and we can, so q1 times q1 is 1, but q1 times q2 is 0, and those terms goes. So we have only v1 times h2 h3 dq1 dq3 plus v2 h3 h1 dq3 dq1 plus v3 h1 h2 dq1 dq2. So this is the surface integral between. So you have to find h2 h3, represent dq1 dq3, and we have your vector v1. You calculate the first part, second, and third part. So this one was the surface integral, but we can I'm going only to express only the volume element, which is very easy. So d tau we call volume element, which is d sigma d tau h1 h2 h3 dq1 dq2 dq3. So this comes with from mixed product. Like for example, we have three vectors a, b, c, and now if we want to find the volume which they make, so which is first we have to find the surface which they make. So a and b, they make this surface. So a cross b, first a cross b. And if we want to find the height of this, so from those vectors which make those, this is the c vector, so they make the volume, something like that. So they make the volume c, so which is we have to mix the product c vector. And same goes here, d tau, which is so first we have to find partial of r, partial of qi, cross partial of r, so dqi, partial of r, partial of j, dqj, dot partial of r, partial of qk, dqk. So we, from this form, we have this one. So those was the metrics, the surface integral, the area element, the volume element, and now so we need those h1, h2, and h3 to write the gradient, the divergence, and those operators which we combine. So for example, this is the gradient of c. So in Cartesian coordinates we have partial partial of psi, or let's take for example the divergence, so you can see more easily the partial of psi partial of x. You can write in I component plus partial of psi partial of y plus partial of psi partial of z in z direction. But if you have something like x is a function of q1, q2, and q3, so you have to find a different form which composes the h1, h2, and h3. So those things I'm going to express in next video. Thank you very much for watching.